And as they say in the podcasts, here I bring you Cornelia Fermu.
Thank you, Costas, for this. It's really nice introduction. So I'm going to talk today about motion analysis. But before that, let me show you some work that is going on in our lab, the ARC lab overall. Well, no. So we are having, the efforts are on motion related tasks, but on two ends. On the one hand, we are looking at action understanding, specifically manipulation actions. So the challenge that we're really facing here, understanding a manipulation action is very difficult, or any action, because it's so complex, so much variation. Deep learning is difficult because you have to capture all the different scenarios, scenes. So here it's really, the challenge is really like, how can we impose long-term relations from the point of motion? And the other thing is motion analysis that I'm going to talk about. It's about the very low level of visual motion. And again, our applications are in robotics in the drone domain. So let me show you a little bit about the first. We are applying action understanding, both in for interpretation of video, but also for on the robot. And here, what you will see here is one of our demos, where there were two tables opposite of each other. On the one hand, somebody was mixing a drink, and on the other hand, the robot was mixing the same drink in the same proportions, but of course with its embodiments. For example, when here the Getcho is mixing with two arms, the robot can only use one at a time. Here first the orange and then the green. And what is going on under the hood are a lot of processes that are running. In this case, we need to build models, 3D models of the scene. We need to, what you see on the left, we need to model and plan the whole robot navigation. For this specific task, we need to model the liquid and its amount, and so on. And here you see at the end, the robot was also garnishing the drink with some lemon and serving it. So this is a big application. It's, of course, when you go into a demo, a lot of engineering work. But what are the challenges really under the hood? I see it's currently, action understanding is to a large degree first from single images and then very primitive motion descriptors. But you can't really understand actions which are so complicated. It's a back and forth between thinking. You have much more models in order to understand and predict. So we have gone these routes together with modeling. Under the hood, the global model is that we represent actions as events at multiple time scales. So at the very primitive things, you're doing the small motion, you move your hand, you make contact, then you move with the object, you let it go in order to, and then here, for example, in making a book stops, you have the little actions, you put things together, and then you make, for example, a book stop at various events. The important thing is there are certain descriptions, like making contact is something that really breaks down an action. So I think three of the main really concepts that can bring us forwards that I have been working on is we need representations that are based on actions, not just static. And one of these is, for example, we have worked on the concept of affordances. What we did, we said, In this manipulation domain, affordances are related to the shape. An object can be recognized by its shape. So we were the first ones to learn, to build shape maps from Kinect sensors. And on these shape maps, we did machine learning. Another thing important as a representation, the hand itself, it contains a lot of information. The grasp type. So we have grasp type classification. Here on the left, you see it can be used on the lower left. It can be used for segmentation because the grasp reveals when actions change. Or in another project, I combined it with forces and then learned combine, and the transfer give, we demonstrated better recognition. So we mounted forces in the recording phase. Another thing I'm betting on, you want to be robust, especially in the robotics domain, use geometry as much as you can. No contradiction to cost us. So one of the things we created is the 3D point cloud by Kostas Tsamboyanis, Cilantro, a very efficient point cloud. And you can do here things like, for example, track an object even when it disappears behind. As an example, you keep track of the object and know its identity. You can compute, we used it for symmetry detection to fill in. Or we used it also to non-rigid registration and to detect topological changes, which again, it's very important to break down the actions. When do things come in contact? When do they come discontact? We also used it to have a description in terms of geometry. This descriptor, for example, is purely based on how are objects geometrically related, left, right. And out of that, we build a descriptor that describes a lot about the scene as additional thing. So the third thing, or here the topological, the contact detection. The third thing is you need things for generalization. One thing we have, for example, done is, while you see in the current database actions are described by some verb, we classified them according to geometry topology. For example, many actions are dividing. So all actions that divide are cutting, chopping, actions assemble, transfer, deform, create, consume, basically are these 6 categories of higher topological changes. And work included like tracking it according to this. And recent work that it can be used in zero-shot learning, where you have a concept from language space. So here it's this concept of generalization, then lets you even detect things you may not have seen. You may not have seen anyone scaling with a Yulu knife, but you have seen other actions of dividing. Well, or another thing is we borrowed this concept from industrial psychology, where they have, which was used for efficiency descriptions 100 years ago, where they have described actions in very small components, separated into the motions required for performing an operation, extraneous motions slowing down, and motions that do not perform an operation. So you come up with these primitives, grasp, release, hold, move, reach, use, that have to follow each other. But you can define now, so any action falls into this subcategory of small events. Now you can define constraints on it. Some things are not possible. And like, for example, an object has to be first grasped or reached before it can be released. That helps you then in getting better segmentation.
Are these rules less from observation or are they called?
No, somebody in industrial psychology is called the Serblix, has come up with this for the idea of automating industrial tasks, making them, and it has been used in other areas. So now here we are picking it up for vision. They are very well studied. Well, so these I think are really these are things we need to do in order to get further on action understanding. A project I'm doing right now is it's about violin education. We want to educate, we want to create software for helping students of violin learn the violin. And together with Irina Muresano, an expert violinist, we're creating this program. First, it's just the posture in the first phase, because students of violin really suffer from this for a long time. This is a challenge for many years to get it right. And the next stage is then to teach certain techniques. In the violin, you have certain skills on the left hand, certain skills on the bow, and certain musical skills that are again standardized by music education. And here then we come into the fine motor estimation that is going to be work. And the fact that interests me from an action point of view is that it's the motion that creates the music, right? And the way you move influences it. So there's this strong correlation. So in the first phase, we're exploiting this correlation to get better pose. When our tool is ready, we also want to do various studies, how they are related and what you can do and influence it. So the second thing is action understanding is the low-level motion. And the dominant approach, as you all know, in motion understanding, 3D motion, the navigation, the whole range of visual navigation, is the called structure for motion or SLAM approach. Simplified, we are corresponding points, we are defining constraints on them, we're enforcing them over multiple views. And the dominant approach is the SLAM technology, where you do this in a probabilistic way and you keep updating correspondence, shape, geometry, and 3D motion. However, there are certain issues, like, what you see out there often is not vision, it's also used laser, which depend on certain sensor ranges. There are challenges with very fast changes. It's computationally very expensive. And it still cannot, this framework cannot handle all moving objects. So our approach in general in the lab has been about, we do not need to make models all the times of the world. For many things we can do with much less visual representation, which is much cheaper. And we have been talking about this hierarchy of competencies. So at the very low end, you have to do ego motion, kinetic stabilization. For that, you don't need to reconstruct the whole thing. Then you need to detect independently moving objects. You need to avoid them and you need to be able to pursue them. So I will be talking now during the next things about these tasks. Then high up come homing. Now you need a memory. And then tasks like landing, where you also need the capability of building your home, building the representation for moving. So let me I will be talking about other tasks. One of these tasks, a very purposive task on a recent paper, the event sensor was used to detect the propellers. A model was built and the very fast motion in classic things comes out very well on an event sensor. As you see now soon. Well, that's what the event sensor sees, which I will be talking about and that you probably know from classes. So now this can be used, for example, in an application where we track another drone and following an unmarked drone, because you see the propeller, you have models. Or for mid-air landing. These are such individual tasks. So what I'm saying, this SLUM approach, most of the computer vision is still, it is still frame-based. We are corresponding points. So in some way we need to process single images and then correspond that, even with flow. But we know from nature, very basic in animals, such as this frog, he cannot see static things. He can only see this fly when it's moving. And there were the experiments, frogs were starved to death because if a dead fly was in front of them, because it's only motion. So motion is actually much more simple. And I'm going to talk about now work on thinking about this, where have we to use motion in a more primitive way. And one of these is the spatio-temporal filters, normal flow, that I have worked on in early days in a geometric way and recently revisited to make it also work in neural networks. The second thing is I'm using also event-based sensors that do not give you static images, but only changes. So we have here high spatio-temporal content in form of events. And the third thing that I will be bringing in is I have done throughout visual psychophysics experiments that actually point to some insights how motion might work in biology. So we have three concepts just to bring us all on the basics. Then we know that when we are talking about this low-level motion, what's involved. The one is usually we talk about, we have successive frames, we compute some image representation. That's usually considered the flow. How are points correlated? Out of that, then we can compute the transformation between the views, which is the ego motion, 3D motion, multiple view geometry. And out of that, if we have that and the flow, we can plug it back and get the scene depths. These are the three concepts. So when I say I computed normal flow it's because you can just get it from the spatio-temporal filters. It's really just spatial derivatives and temporal derivatives combined. And let me show you here this an illusion that shows there is a problem in flow estimation. This pattern, you may just see it moving if you look at it, or I will jiggle it for you. It's just like a jiggling, and you hopefully see the inside moving relative to the surrounding. So why is this case? When we talk geometrically about this concept of flow is really an estimation. It's the correspondence between points. But when the first input that we get from a stack of images, we only can compute locally at most cases the motion perpendicular to the strongest gradient direction, to the edge. And that's just a 1D component. We termed it normal flow. So when we compute flow, the very simplest way I'm trying to explain the illusion is we are saying we have multiple such normal flows. Let us put them in one point nearby. They all come from the same optic flow. So each normal flow provides us one constraint. We can say the optic flow is perpendicular to it. Another normal flow value gives us a constraint, and we're getting at the intersection the flow. Or if we have multiple, we can add them on, and they all should intersect in one point. All these normal flow vectors we get from a small neighborhood. That's basically what optic flow estimation is. Of course, many more constraints now added. But in the presence of noise, they're not intersecting these lines, and you do an optimization, you find a solution that is closest with respect to some criterion, usually least squares criterion. And it turns out that the least square solution in the presence of noise is basically not the correct one. There is bias. And the idea being, so if you have the normal flow, it means the flow component, the normal flow in the direction of the gradient. and you get this 1D constraint, IXU plus I, sorry, 1D constraint on U and V. And you combine multiple such constraints, you get a linear system in a neighborhood. That's what you solve. We can say we have a system AX is B. So the idea is now when we solve a system AX is B, but if we also have noise in A, which means the normal flow is not estimated correct in direction either, and there could be error in length, the least square solution would be this standard way, but it is biased. That is very well known. So usually least square is unbiased if errors are only in B. But if they're also in A, we have a bias. So what we get is the correct solution plus some additional term, and that term depends on the texture. And it's usually an underestimation. And we can explain, I used it to explain by analyzing this texture matrix A prime AT, which is the texture matrix. So you can predict what the error would be. Intuitively, why is this the case? So in the 1D example, let us just take the 1D example, why it's an underestimation. So we have AX is B, the solution would be B over A. If you have a few examples, but there's error in it, so we have some estimates that are over, some estimates that are under. There could be error in B too, but that doesn't matter. This square takes care of that. Then the solution would be the sum over the AI, BI over the sum over the AI square. Now add in the noise, and what you get is 3AB over 3A square plus some additional noise terms. So the lower term is larger and we get an underestimation. That's the intuition. And this takes, of course, over into 2D. So it's a quadratic terms in the equation that give this bias. So on the basis of this, I have explained many illusions, something like this. So in the Auchi illusion, what is the case? Let's go back. We have in the inside these bricks that have a texture with vertical bricks. So there's many more gradients to the horizontal direction than in the outside, where there are many more gradients in the vertical direction. So you get a different bias in the inside and outside. So usually your system uses general motion, ego motion from the outside. And now you have, if it estimates it from the outside, then the inside has a relative motion. And that's what you experience. So here's the residual flow, the flow computed that you would actually get with the least squares. And we have looked in other estimators too. The problem is, if you want it to really correct, you need to get the error statistics, which in general is hard because it changes. Actually, the system may adapt and then partially correct. But so I have many illusions on my website. The same principle applies also to points here. You see the illusion best if you go back and forth. So then you see these rings rotating. So bob a little bit your head back and forth. And again, the outside has a different bias than the inside. So that's why you see this additional rotation. And please enjoy, if you haven't, some illusions. So for a long time, I did this a while ago and revisited recently, and actually neural networks give it too. And the reason is because they do actually a piecewise approximation, linear approximation of the function. But for a long time, I thought, okay, bias, which is basically the aperture problem. Well, it's a small problem. The real problem for flow estimation is the depth continuities. But we are in 2022, and you look at the optic flow algorithms, they're doing very well at boundaries because they're incorporating so many processes, warping functions over global region, considering the occlusions. So the second problem, which was the real problem, the depth discontinuity, is kind of gone away. And left is the bias problem that we still have in modern deep learning algorithms. So I'm going to show you now recent work on including this idea of normal flow directly into the 3D motion estimation pipeline. Why we want to do it? So the current learning approach, the standard is really we take from single images steps, from multiple images, we compute pose, and then we estimate on the basis of this. That gives us the flow on the basis of which we can align and feed it back to learn in a self-supervised way. But of course, if you learn pose first, you have overtrained and it's difficult to generalize. I mean, okay, the classic approach is that we eliminate the depths from the equation, what we have been working on for a while, which is the Ebola constraint. And then we have worked with depth independent constraints. But flow estimation does have some problems already. So we had earlier on worked with normal flow with geometric constraints, interpreting this in some way and then doing half voting and things like that. So what I want to do now, really estimate motion first robustly with this normal flow and then do other things like depth estimation, flow estimation, and segmentation. So how do I do this? Just to get you the very basic, when we talk about 3D motion estimation, we say it's due to a translation V and a rotation omega in space. And when we project this on the image plane, the image motion, then it gives me an equation that is linear in V, but it's divided by the depths, plus a rotational component that is linear in the rotation. So that's easy, it doesn't depend on depths. And we deal with it in the classic constraint of the Ebola constraint. We say take in the flow case, take the flow, subtract from it the rotation, and that should be then perpendicular to the translation. So geometric, if we have the flow, we have the translational direction if we knew the motion, but we don't know what the depth is. So we subtract from the flow the rotation, and then we minimize to that line that gives the translational constraint. That's the Ebola constraint. But in this case, we have two components in the flow component. We have two components. We don't have that in the case of normal flow. For example, here, what is normal flow? For example, if the drone is going down, it has an expanding, it would see the world expanding. And you see the optic flow would be the blue vectors, but the normal flow geometrically means only we have the component of that flow perpendicular to the gradient. That's why we call it normal flow. So here's the idea. So in the case, the flow equation is it's A times V over depth plus a linear term in omega. If we have the normal flow, we basically, from our geometric interpretation, we say that normal flow is this times the scalar product on the local gradient direction. So we multiply this both in the translation and rotation. And what we can say then is that, so take the flow, subtract the rotation, then we have the translation. We only know the depth is positive. That we know for sure because it's in front of the camera. Nothing else. So we can still say this translation times the derotated flow have to be greater 0. That's the positivity constraint, or used in chirality constraint called in the literature. So let's call it rho of x. And early on, as mentioned, we did various things of geometric interpretation to somehow vote on it and find it. Now, recently, what we said, instead of implementing it, just say, where is it positive, where is it negative? Let us put a function over it, and the simple functions is the ReLU function. So we can say, when it's negative, we punish it with minus x, and when it's positive, then it's fine, 0. So we put this ReLU function over it, and that's what we're going to minimize. And In reality, you can't use ReLU because it's discontinuous. You have to make it continuous. So in the deep learning, we used the so-called GELO function, a smooth approximation of it. So now you have a function that you actually can minimize. And so the first work was then solving a classical optimization, the normal flow constraint with this function. And then after you got from that ego motion, use smoothness constraints on the reconstructed depths in order to estimate better motion. And we found already it works better than classic optic flow. But currently you want everything in a neural network. So the idea is that we can use the so-called differentiable programming formalism, and this way embedded in a neural network. We formulate the positivity constraint in a forward pass. You solve an optimization. You can solve an inequality with interior methods. And in the backward pass, due to new work of Stephen Gold, we can now embed minimizations of any kind, constraint minimization, non-constraint minimization, minimizations with inequality constraint. And all you need to do it is compute the derivatives of the known with respect to the unknowns. To design a layer for the backward pass. So in this case, we said we estimate it iteratively. So we start with an estimate and then improve this via the normal flow equation from what we have to get a better estimate and use this differentiable programming framework. So the whole
Cornelia, why didn't you use this constraint just as a loss? But now you use it as a layer of the network, which has to be differentiable. The output of the layer is the argument of this, right? And
I mean,
why
you could. I mean, it's very weak, right? I mean, we used it in a forward pass with the loss, but the positivity constraint is weak. It's not. It's just positivity way weaker than. Right. So we do actually in the forward pass, but then refine it iteratively using the normal flow. So we get the normal from that estimate. You can implicitly estimate depths, plug it back to refine. So that is, yeah. And this way we improve. Yeah, okay. So the whole architecture is then, there's a normal flow network that works like a flow network, but only on normal flow. So that's a new thing. And we trained it supervised by considering the projection on the normal flow. And that stays, it's trained and then stays. There's also a network that just is initializations on both networks. Just like in any optimization, you gotta have some starting point, a rough estimate. And then you use this differentiable layer using the normal flow. When you have an estimate, you can implicitly estimate depth and refine it. And you keep iterating. I mean, you train it, and in the iteration, when you run it during testing, what you do is you run it through the forward pass, through the classic, to the optimization that you have, and then you have a few layers, just a few passes. And for this, you have a self-supervised loss, the loss of normal flow alignment. So first, deep learning, the current optic flow networks, they do still have a problem with optic flow. Exactly that bias that I explained before in the illusion. So if you see here state-of-the-art network, cell flow, light flow, in a texture like the brick, like the Auchi illusion, they're not doing well. This is the error. The color shows the error. Here zoomed in, whereas the normal flow network has way less errors because it only considers the gradient. So on the normal flow network itself may be used now in various ways. And here I show some results from the paper. So it was trained on the Tartan air data set on a subset and then evaluated on these two things, abandoned factory hospital. And you see here the normal flow net comparison. So our normal flow network does really well in the projection endpoint error. Now here is a video showing the absolute trajectory against SOTA deep learning. Tartan VO. And you will see our trajectory again is pretty good. It's the red one, which is more accurate than the black one. And now to some results. Here is a result of the relative pose estimation against state of the art. So the deep, so what is exactly done? It's on Kitty. It was trained on Tartan Air, but trained on Kitty. So generally, deep learning does very well in estimating translation. And the classic techniques, orb slum or another slum here, they do much better on the rotation, the geometric methods. So it's hard to beat these geometric methods on rotation, but ours is still doing very well, definitely much better than the translation methods. And here you see the comparison in the rotation error where we are just superior. Here are some noise studies. If you add noise in, how it affects. So here, normal flow is much less effective than optic flow. And the comparison goes against a method goes, our chirality. The bilevel optimization, that's basically also a method by Gold who implemented optic flow in this framework of deep learning, but with the Ebola constraint. But that performs much less.
Does your step also always nearly on top of that, like pose optimization at the end? It does look close.
No. This is just no, it's not. It's just relative pose. Of course, we estimate the factor to do the full pose estimation, but not the engineering, just the factor. Yeah, okay. Well, a little speculative, I'm coming back. What I'm saying, there is this pipeline there, image flow, 3D motion, scene reconstruction, the processes are linked and we solve them linked. What I'm saying is let's change the pipeline a bit. Let's do 3D motion first and then do correct image motion. And I have here some illusions that I did long ago, and they do show some that it actually seems to be that way. So just for you, for the geometry, a translation flow field looks like this. It's a point and everything is emanating for it, scaled by the depths, how long the vectors are. A rotational flow field is basically conic sections in the image. See, points move around conic sections. So look at this illusion. It's the Levian illusion. And what you see is when you look at it a little bit, hopefully, you see some additional motion inside the rings. So this is an illusion in the Louvre. And very long ago, I started working when you set up these black lines such that they're either related to only rotation or only translation. So here, for example, on these black rings, all you can compute is the motion perpendicular to these patterns, the black and white. You cannot estimate anything of the forward component parallel to it because you have no gradients. Then you get this illusion. And the idea being, and then we created also other such things exactly when there's only, where the black lines are related to either rotation or translation. And then you have bends perpendicular to it, like this. This is my illusion, or this. My illusion, you also see these patterns. And it works with that fact. Whereas when I set it up, not related to rotation or translation, but just general, like here, some sinusoidal thing, and then to put rings or patterns perpendicular, we do not get the illusion, which I have argued that we really estimate 3D motion first, and then And there is also some interpolation going on inside the ring. And then when you come back in order to do, then you do in a comeback using that 3D motion already to do the segmentation accurately. But at that point, since you had moved on and it's a new motion, the illusion is caused by eye movement, you cancel it out. But in the case of the rigid motion patterns where you can't cancel it out because you don't have the information, it stays because there's ambiguity. Yeah.
Could you remind me, they assume the eye micro movements in order to explain that?
Yeah, actually it has been shown in some, I mean, I had hypothesized it and then it was confirmed that the illusion is related to the small eye movements, the microsaccades, yeah. It's caused by them, yeah. Mm-hmm. Yes, yes, you should keep your eyes still. You should keep your eyes still. And in this still movement, yeah, I didn't pass that on. In psychophysics, when we look at this illusion, then when we fixated something, we have small eye movements going on that are involuntary. They classify them into 3 categories, depending on their size. Very small micro movements, then so-called drifts, and microsaccades, and they go on involuntarily. And it has been shown also that they are estimated visually. We compensate for them. You're not aware of them. You stitch your model together, and it's rather easy because they are due to the eyeball, so it's mostly rotation, so it doesn't depend on that. I mean, you still have to separate all this. I don't think anybody knows because we're also moving at the same time due to translation. But it has been shown through psychophysics experiment that they are estimated visually, not through your inertial system. So another topic is motion. I have also worked with the event sensor. And okay, so you know it probably from Costa's work, that sensor just, the way it is, each pixel has its own circuit, works asynchronously, and it's set such that when the log intensity changes by a certain threshold, you get an event. But you get that event. Here's, for example, visualizations of what you get. We usually visualize them as images by accumulating events over a certain time interval into one frame to give you a visual impression. You get basically the edges at the boundaries and also at the texture. You get very high dynamic range. That has been exploited a lot. You can go from day to night because of the logarithm. You get very high temporal resolution, very low latency, and it is ideally a low bandwidth signal because you only record the changes, so made to fit for spiking architecture. Of course, on the other hand, currently we still have to deal with quite some high noise. But in principle, the sensor is well suited for real robotics. And I have done various works on motion segmentation. Intuitively, you get this high information at the boundaries. So that's why it's well suited and it should be there. So here, what you will see is on the 2 images, on the 1 image, just a display, a classic image where we shoot an arrow on the, you can see nothing in the classic image, but you see it in TBS. So now the arrow is coming and you see it on the right in TBS. So it can capture also high motion, very fast motion. So a few works we have done, classic, learned, a data set, and also we do segmentation. One of the things is when I started, the local thing was already done, the flow, the normal flow, the image compression. But we can also, that's where I want to go and towards going is We can also deal with them as clouds in 3D, space-time clouds. So in a work that is quite used well, what the idea is, because of the large noise, it's local estimates are not very accurate. So instead, let us do a motion segmentation by globally compensating the motion, which can be estimated more robustly, then see what doesn't compensate these independently moving objects. And in the first work, we used just a 4-parameter model, well known in the biological motion, XY translation, circular rotation and expansion. Shift, radial expansion. So what's done is the best motion, so you grab a time interval within this time interval, you grab the data, all the data, and you say, if I warp back with my model, my 4-parameter model, each point to at the beginning of time, I say within that small time interval, it's linear, then it should totally align if it were ideal, if it were correct. So that's the concept behind. And you can enforce this both in various ways. People usually do something like they count the events and then define measures on that. But you can also do it on the timestamps, that the timestamps have to be aligned. And on that, you can do a fast optimization because the timestamps basically at the boundaries go in the gradient direction of the change. So that was the idea. We warp the 3D events. The warping is done within one slice in the analytic method to the beginning, so in 3D. And then we down project it and do measures of space and time. Like here you see on the left, this is the image and this is the time image is color coded. So if you compute the gradient on that time images, that tells you already in direction you have to, the motion is the 3D motion, and you do a few iterations on it. And then you align it to bring it in alignment. You optimize for the best alignment. And the idea is what is motion independent movement then isn't aligned and stands out. And early techniques, we did some simple clustering and created some data sets that really can capture also now challenging scenes, like in front of the net, if you look at it, very fast motion, strobe light. And recently, the segmentation is still hard. What stands out, what is blurry to cluster is not a trivial thing. So Chetan included as a second process point tracking. So we align and then we track the points and we say, these points have to follow, clusters of points have to follow this 4-parameter model. It's a simplified model, but if it's in a small region, it's okay. It's good enough considering the error. So you cluster on the point motion within groups, within this, and then you do a merging and going on these clusters. You apply the estimated motion via alignment again. If it aligns kind of good enough, when you merge two clusters, then you cluster them. If the error is too large, you don't cluster. And with this, he got really very good results. Others works is, we also are interested, we included this in the pipeline of 3D motion estimation, like it is common, where you estimate it now from time slices steps, and you estimate the pulse network from multiple slices, and you align now the flow. When you have the pulse and when you have the depth, you kind of know what the flow is, what the alignment is. You align for that in a self-supervised way to learn the ego motion, fully self-supervised.
But here for the flows, you didn't use the optical flow, right? So you estimate directly from the image.
Yes. Mm-hmm. Yeah, it's directly from the image. I mean, not images, I mean, event slices.
For events,
Yeah, event slices, and we used multiple scales. I mean, different slices also combined, right? Different distances, yeah. But it's not, it's relative pose, and it's really the slice is aligned. It's not what I said before, the 3D to make it. I mean, in this work, it's to make it work the more image way technique. And yeah, okay, the approach does well. One thing, it inherits from the camera, it transfers from day to night. I'm not going to go into detail, but the architecture is very lightweight. We took advantage of the sparsity of the data that it was designed for, with very good results. And the trajectory, you see here some of the results. Here, event input, ground truth, estimated flow, depth, and the output of the depth network. And you will see that the network actually, from the UPenn data set, the network actually fixes sometimes the errors in the range sensor, which is not correct, very close by. The network gets it better. Well, so this is a demonstration. You definitely can take advantage. It transfers from day to night, which is due to the camera, and the network takes advantage, taking advantage a bit of the sparsity. Also, it's in a deep learning framework, but it's way more lightweight than other architectures. What we did, we created this data set. It's a nice resource, EVIMO. The first version, how do you create this data set, was really, we scanned the room with the RGBD sensor in the first thing, and we high resolution scanned specific objects, and we tracked everything with Vicon markers, with Vicon system and markers. So we know exactly the geometry combined with the depths, and then the masks come out independently. So, but now, so you have now actually a data set where you know the exact 3D motion of all the independently moving objects and the ego motion. But the second data set is even better, that we just put out last week. It's out, but now it's categorized and organized well, where we use two prophecies, a Samsung, also a prophecy with grayscale. So it's this whole rig that was used for recording. And now the RGBD scanning was still an issue. To align it is not so accurate. So now we really focused, we did a whole board that was the scene, that was all high resolution scanned. So now you have very accurate depth of the estimation of that scene. And there are scenes for ego motion, and there are scenes for independently moving objects, such as, for example, the here below with the masks, due to because we have the geometry of it's scanned, we have the Vicon 3D motion, the masks come out, everything by itself, all the tools are there, and the depth maps. So, well, and with that, we also designed an independent motion detection network that, however, still with the first, we don't have enough data. So it's still partially trained supervised, where the idea being of the independently moving objects, we pointwise estimate 3D motion using the data that was recorded from the data set. So for the specific objects, we have masks and we have the ego motion, and we trained the network then to spit out pointwise 3D motion on which you can cluster them. So that component has been trained, supervised. Well, here are some results that you see: the TVS input, the ground truth depths, the estimated depths, ground truth pose and estimated pose, which is pointwise, as I said, quite well with this method. I mean, individually, all the moving objects estimated. with ground truth ups with the color corresponding to the correctness, and the mask, which is also, it gets all the objects, of course, a little blurry at the boundaries, just the learning approach. Well, a simplified version of that, not with full estimation, but by estimating the motion model as a homography, was used in a drone task where the camera was equipped with a down-facing camera, a front-facing cameras, and all computations are done online on the NVIDIA TX2. So you don't have that much computation. And the way this was done specifically is that for the down-facing camera, a homography network was trained, which actually used in this case synthetic data, and then some kind of a blur network to make it like the data that you get in real. So on that, the homography was trained, and then the independently moving objects, like done before, as individual outliers with the individual steps, individual 3D pose. Okay, so here's the demonstration. Implemented on the drone now. This drone runs the homography network and detects the moving objects and dodges to avoid them. You see what the front camera sees, that it sees the objects. The background camera has the 3D motion. Well, yes, and then it's the pursuit task. And we also, most recent work focuses now on going and really studying the point cloud in 3D, which is ongoing work. So I thank very much, really, the people who have contributed most to this. Anton, Chetan, the new normal flow network, Zhengzi, the flow network, Levi, now the new EDI-MOU, Nitin, who just got a faculty position, did the drone work together with Jahad, most of it. So thank you.
Results, Cornelia. That was really great. I want to introduce the two panelists here who are going to take questions both from the audience and the web. This is Ken Cheney and Kendall Quinn.
We're going to take from Fernando.
So one of the students on chat, Fernando, asked, how well does the network generalize to different settings? We observed that for EV DodgeNet, the setup used and the objects to segment are the same as used in training.
Does not generalize completely, but it does generalize very well, especially the homography network, because yeah, basically you're subtracting the homography. So things still come out, you can detect. Yeah. But of course, yes, and the other network also, there's no doubt this has been trained self-supervised, but still the mask training makes it pretty good. Okay, so the next step is to include the segmentation with this differentiable framework to formulate those constraints, to get geometry also into segmentation. Otherwise, we can't do it. Yeah, we can't handle everything. And also more geometry, longer frames, tubes, more frames. Include those constraints.
So I'm wondering why for the pose you didn't use like first the flow estimate and then use directly your differentiable module in order to estimate the pose, and you did it directly from the events, or even from the, I think previously it was even from the images.
Why from the pose event we didn't? use.
Why didn't you first estimate the flow and then use the
Okay,
estimate
for the
pose from
normal
the
flow network, it's clear I didn't want to use, right? I don't want to use flow, right? Okay, so yeah, okay.
So you have two branches, one depthnet and one posenet. And in none of them at the beginning you use the flow. You just estimate them directly. You regress directly the pose from the pure stream of data.
Yeah. I guess you could have a flow network first estimate both in the deep learning network, but then you still have to go back. Now you have a better, maybe a better pose, but the flow networks, at least with DVS, weren't that good to that accuracy that was found. So I think the step was skipped. But in any case, you would have to go back to a line again after you have both with flow, right? It could be, I think we tried, but it didn't work.
So this is about the really interesting motion illusions that you showed earlier in the talk. So do we have reason to believe that the brain, for example, is doing least square error estimates, and that's what causes this type of bias? Or is there basically no solution at all to producing an unbiased estimate?
I think, okay. All right, I think that, I mean, I don't know if it's least square. I believe it's, you could do other estimators like L1 or total least squares. But I mean, even to do total least squares, for example, which supposedly you can correct, you would have to get an estimate of the noise to correct it. So I actually did some papers on it's difficult because the scenario changes, right? So you would have to estimate always the noise situation. So the ideal situation, bias is not the only thing we worry about. We also have to worry about variance, right? So what you minimize is a combination of bias and variance. And so looking at that, I analyzed it once and came up with the ideal thing would be to do partial correction to minimize this error. And I think it's happening with many illusions when the stimulus stays the same and one can stare at it, it's getting weaker. It's not going away. So I think the system does partial.
So over time, it adapts to the statistics of
I think so when the scenario doesn't change. I think the system does the best it can. So on the website, you can also see it's not just a factor of flow estimation. It's also of point estimation. It's an estimation problem, line estimation, and also 3D. I created some 3D illusions where also we have the effect of slant underestimation. We always think it's more front parallel than it is. So if you set up some textures in such a way that you can induce it, you actually get things warping, you can see.
I see. So do you, in those cases as well, is there kind of an analog for neural nets? Because
so yeah, we actually, I mean, okay, I have just recently, and it's written up, we tested it for flow, and yeah, coming back to some existing results, you get the exact things. You get also the illusion, and the intuition seems that okay, people have written paper, somebody has written paper. The neural network basically estimates a piecewise linear function, and that would be the reason why you also get it in the network. And you see it on our results too. That's the only thing that's still left, and I don't know if it can be fixed. It's back to the aperture problem in some way, yeah.
Thank you.
I mean, definitely if you train for specific scenarios, but then you lose on others.
I have a follow-up from Fernando. Actually, he wanted to also thank you for the amazing talk. So not all the event cameras are made the same, and it was very interesting that you used or a variety of brands or mixing the different brands in the same data collection setup. Have you observed fundamental differences between the different event cameras that may affect the performance of your algorithms and networks?
You know, I think the Prophecy and the Samsung are basically equivalent. Yeah, they're both very good. Yeah. Okay, there's some Prophet. I mean, that's the main thing. I mean, that these are the high resolution and new things. The Prophecy now has all these key. They has a lot of software now also available that they give. Flow estimation, basic segmentation, nice toolkit. So I think it's easier to buy at this point.